Questions about anything from last time? Well, today I'm going to talk about Fejér's theorem and Fejér's kernel. And it's the first example you might see of a thing that's going to turn out to be very useful in your more advanced analysis classes. Fejér's kernel is an example of a good kernel. Most people would agree, and Stein actually uses that as a technical term. We've been dealing with a kernel, which I would call this a wonderful kernel, but it's not a good kernel. And I'll explain what I mean by a good kernel as we go along today. It's a wonderful kernel, but not a good one in the sense of Stein. Okay, and I graphed a Dirichlet kernel for you a while ago. And it looked like this. Let's see, it had a gigantic peak at the origin. And it went negative and then wiggled and sort of fizzled out as you go that way. Okay. That's the Dirichlet kernel. So the good thing about it that we used in the computations last week or last time is that the integral under that thing, this is a signed area of the positive areas minus the negative areas. That's equal to 1. That's a nice thing. Good things. There's one good thing. It's big at the origin. That's kind of a good thing. Really big. But it turns out that those integrals, if you integrate the absolute value of that thing, take the absolute value here, that goes to infinity as n goes to infinity. Okay, and another bad thing is it's not positive. dn of t is not it's not greater than or equal to 0 for all t. Those two things are mean that it's not a good kernel. Okay. And the Fejér kernel, which we'll study today, which comes up in a very interesting way, is a good one. Its graph, let's see, what is it going to be? I'll write a formula for it in a minute. It's going to have a great big bump at the origin, kind of like the Dirichlet one does. But then it's going to remain positive, and it's going to get real small out here. Okay, so it's going to be big, have a great big hump. It's going to be greater or equal to 0. There'll be some zeros, that's okay, but at least it's greater or equal to 0 like that. We're going to write for this thing, we'll call this Fejér kernel Fn of t. And the great thing is, let's see, the good things. The integral from minus pi to pi of the Fejér kernel is going to be 1. F has a big hump at the, is big, near 0. And it's positive, that's going to be a good thing. Or I should say non-negative for all t. And it's going to go to 0 outside of any other small interval about, so Fn of t goes to 0 uniformly. Outside an interval like minus delta delta. So that means that area is going to be concentrated at the hump, at the gigantic hump. And that's going to make this something called a good kernel. Oh, by the way, I'm not going to dwell on constructing a nasty function. But Stein, so an important example, you'll find it in the book. Stein constructs a continuous 2 pi periodic function that doesn't converge at a specific point. So a continuous 2 pi. So it's been kind of exciting. We've been getting convergence in various cases, and we might hope to get convergence for general continuous functions. So there's a continuous 2 pi periodic function whose Fourier series doesn't converge. Whose Fourier series does not converge at some point. X naught. Okay, so that means it might be kind of hopeless to try to get a theorem that says Fourier series converge in that generality. So it's definitely hopeless. But here's the big idea. We still want to approximate continuous functions by trigonometric polynomials. So this was Fejér's big idea, which was a brilliant idea. And it turned out to be so nice and clean that it's why I want to do it right away. So let's see. We have this. We had these no. What am I saying? Okay, so we have partial sums, Sn of t. That was the sum from minus n to n, and we write it in the complex notation. It's shorter and sweeter. Okay. And the CNs here are what, now I'm using this notation of Stein, it's the nth Fourier coefficient of f. Okay. And we'll assume that f is continuous and 2 pi periodic. F is continuous. And we know from Stein's example, I mean, he's not the one who discovered it, but it's described in his book. So we're going to assume that f is continuous and 2 pi periodic. Well, Fejér knew that maybe the Fourier series wouldn't converge to f, but he had this brilliant idea, is to consider the average of the Fourier series. Of the first n, first capital N partial sums. Partial sums. Let's see what I'm going to do. Let's see, when you do the first n, you're going to get, let's call, and this is a, we'll call this sigma n of t is going to be, let's see, the first one would be s sub 0. I'm going to change to x's. X. S0 of x. And the next one would be S1 of x plus dot, dot, dot. And I want n of those things. I'm going to divide by n. So to get n, I would only have to go to S sub n minus 1 of x. Okay. Of course, that x naught is just a constant. S naught is just a constant. So that's probably a mile away from f. But hopefully these get better and better. And even though they might individually not converge at some x, their average is actually going to converge. And Fejér was able to show this. And so let's see, when you play around, remember we were able to write, when I did that calculation, I was able to write these partial sums as the 0th Dirichlet kernel plus blah, 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 out to the n minus 1st Dirichlet kernel over n times f of x minus t. Okay. And so I just taking the using that formula that I derived 2 times ago, and this is what Fejér called the Fejér. I don't think he called it after himself. Somebody else did that, but this is the Fejér kernel, Fn of t. And you know all those things were geometric series in e to the ix. Or IT in this case. So when you write it, it's kind of it's not terribly messy, but these are just, you think about it, combining those geometric series probably isn't going to be terribly hard. Combining geometric series in e to the it and e to the minus it and being clever like we were with the Dirichlet kernel, in the algebra, might lead to something. And Fejér sat down and did it, and sure enough, he got a beautiful formula for the Fejér kernel. I'm not going to do it in class today because you've seen something just like it in the Dirichlet kernel calculation. So he got that the Fejér kernel is 1 over 2 pi n sine squared nt over 2 divided by sine squared t over 2. And if you graph that thing, you get that picture, the graph I drew in the beginning. Those are positive. The sine t over 2 is never 0 except at the origin. And at the origin, you can use L'Hopital's rule and see that that converges to something big. So let's see. I'm going to assume this for the moment. My Fejér kernel has this beautiful formula. So the key properties. Let's see. Fn of t is greater or equal to 0 for all t. Check. You just look at the formula and see that that's true. We're going to have to define it at 0, but that's not hard. That's going to be L'Hopital's rule. Let's see. So that's key property number 1. Key property number 2 is that the area underneath that graph of the Fejér kernel is always 1. And the proof of that is easy. All the Dirichlet kernels do that. And I'm taking an average of Dirichlet kernels. So the dn of t's do that. So if you add those up and integrate, you get 1 plus 1 plus 1 plus 1 n times, and then you'd have to divide by n, and that would give you 1. So that's a very straightforward thing, knowing that the Dirichlet kernel have unit area. Okay. 3, the limit as t goes to 0 of that formula is equal to n over 2 pi. And that goes to infinity as n goes to infinity. And the proof of that is L'Hopital's rule. You just do it. It's very simple, L'Hopital's rule. Number 4, even though it's getting gigantic at the origin, it's going to 0. So outside any interval, so I'll take the outside of the interval from minus pi to pi, let me say, minus delta to delta, when delta is something less than pi. Think of delta as being small. So outside that interval, Fn of t goes to 0 uniformly. On, let's see, what's the rest? The rest of the interval there would be minus pi to delta union, minus pi to minus delta union delta to plus pi. As n goes to infinity. Let's see okay, I've been telling you the proofs as I go along, so I don't have to prove the previous 3, but number 4, I'm going to have to show you. So let's see. The only problem when you think about number 4 is that that sine squared t over 2 is 0 at the origin. Okay, so if you think about it, what does the graph of sine t over 2 look like? Here's minus pi, here's plus pi. Sine squared t over 2 is positive, and it goes like this. It's 0 at 0. So that's sine squared. That's the thing in the denominator. Okay, and if I have a delta here, how about a minus delta and a plus delta? Darn. Ah! How do you, instead I'm going to do it like this. I'll have my blue thing look like that. And now I'm going to copy it. Now I'm going to pull it inside out. See if I can make it about the same distance. That looks about right. There. That's symmetric. So according to that picture, let's call this spot right here M. Then we see that sine squared t over 2 is bigger than or equal to m outside that interval. And so what would I get here? I would get fn of t. That would be 1 over 2 pi. Here's the important thing. There's an n here. That wasn't there in the Dirichlet kernel. But then, well, these things are positive. So I don't have to put sine squared nt over 2. That's always less than or equal to 1. And here I get a sine squared t over 2 in the bottom. That's going to be less than or equal to 1 over 2 pi n. A 1 on top. And now I know the bottom thing is bigger than or equal to m. So that's going to be less than or equal to 1 over m. And of course that goes to 0 as n goes to infinity. And the important thing is because of this m right here. That wasn't there for the Dirichlet kernel. And that goes to 0 as n goes to infinity. When t is outside that little interval, minus delta delta. Questions about that? Okay, that's going to be useful to us. Okay, and those 4 things are exactly what's meant by a good kernel. A good kernel satisfies something 1 through 4. So Fejér is a good kernel. And here's Fejér's theorem now, which is a biggie. Very important in the study of Fourier series. So Fejér's theorem. If f is continuous and 2 pi periodic, then the Fejér things go to f uniformly in R. So it's surprising. Taking averages of Fourier series makes them converge a whole lot better. If f is continuous and 2 pi periodic, I'm going to whole real line. Then the Fejér things. We use the word trigonometric polynomials. That Fejér thing is a trigonometric polynomial. So these trigonometric polynomials are going to approach f uniformly on R. And I'll put an exclamation point there because that's kind of mind-blowing. Well, we've done this work already, so it's going to feel quite familiar to see it. But this time it's not going to be nearly as technical. I had to do some fancy, wild things when I looked at this kind of thing for Fourier series. I had to use Bessel's inequality, which seemed like a sneaky trick. I don't have to do anything like that when I do this because of the goodness of Fejér's kernel. So let's, when I write phi n x, sigma of x minus f of x, well, remember, the sigma n was when I did the change of variables thing, f of x minus t dt. And then you remember when we subtracted off, let's see, I did this before. This thing now is, I wanted to put something that looked, I want to represent f of x as something that looks just like that. So this, I realize, is, this is 1. Okay, so that thing is 1, and if I multiply it by f of x, you realize, oh, that looks very much like that expression. And so I've used the key fact about a good kernel that this is equal to 1. And so now I can write this under one integral. That's going to be the integral from minus pi to pi of fn of t times f of x minus t minus f of x dt. Okay, that's feeling just like we did for the Dirichlet kernel. And now there's two things. That fn is big near 0, but that other thing on the right is going to be small near 0. The f of x minus t minus f of x, because of continuity of f, I can make that small. And when f is not, when it's not big, well then outside some interval, that one's going to be the small one, and the other one won't be big, but it won't be too big. It'll be controlled. So the brilliant idea is I'm going to split this into two pieces. An integral over a small minus delta to plus delta of fn of t times f of x minus t minus f of x dt plus an integral on the rest. So let's see, I'll write the rest of the integral. Integral from minus pi to minus delta plus the integral from delta to pi of the same thing. Okay, so this is the small one. And this is going to be the small one. And that's going to lead me to two things that I add up and get something that's small. So let's call this first integral I1. And the second integral I2. And now I need to analyze those things. This is a classic argument that will come up again and again, especially if we're going to study PDE. So let's let epsilon be bigger than 0. F is continuous on minus pi to pi. That implies that f is uniformly continuous. And because it's 2 pi periodic, so it's uniformly continuous on minus pi to pi, and that implies it's uniformly continuous on R, since it's 2 pi periodic. So remember your theorem from Math 341. If you're continuous on a closed compact interval like that, then you're uniformly continuous on that closed interval. Okay, so this implication is because of 2 pi periodicity. Okay, so now that's where I'm going to get my delta from. So there exists a delta bigger than 0 such that f of x minus t minus f of x, I kind of want that to be less than epsilon over 2 because I've got 2 integrals to mess around with. When absolute t is less than delta. And that's independent of the x. So that's important. Independent. Because that's the uniform continuity. Independent of the x. Okay, so now first step 1, I'm going to estimate integral 1. That's they're both easy, but this one is very easy. First integral is less than or equal to, you have a minus integral from minus delta to plus delta, and then I'm going to take, when I put the absolute value under the integral, I realize I'll have absolute fn of t, but that's the same as fn of t because it's greater or equal to 0. So there I've used one of the good properties. Here I get f of x minus t minus f of x, and I integrate dt. Okay, this is less than or equal to epsilon over 2. And so this whole thing is going to be less than or equal to epsilon over 2 times the integral from minus pi to pi of fn of t. But you know, I know that fn of t gets gigantic at the origin. And so you say, oh, darn, this isn't going to work. But because this is a positive kernel, a non-negative kernel, this is less than or equal to the integral from minus pi to pi of fn of t dt because of the positivity or non-negativity, because fn of t is greater or equal to 0. And this is equal to 1. And so we get that I1, the first integral, is less than or equal to epsilon over 2. That's very promising. Okay, so now I got to mess around with the other integral. And it's going to also be very straightforward. Let's see. So before we continue, note, f is continuous on a compact set, minus pi to pi, meaning closed and bounded. So f is bounded there. So remember, being continuous on a closed interval means it's bounded. let's say that, so being bounded means absolute f is less than or equal to something, m, on minus pi to pi. Well, 2 pi periodic means that I get it's bounded by m on the whole real line. So 2 pi periodic implies that f is less than or equal to m on the whole real line. Okay, so in particular, let's estimate f of x minus t minus f of x would be less than or equal to f of x minus t plus f of t, f of x rather, and that's less than or equal to m plus m equals 2m. So, I'm going to use that in a minute. Let's see, now I get that I2, that's going to be less than or equal to, I'll have the integral from minus pi to minus delta plus the integral from delta to plus pi. And then when I take the absolute value underneath, I would have fn of t here. That's positive, so I can take that one away. And here I'd get absolute value of this dt. And this, remember, is going to be less than, outside that, oops, did I say, I can, yeah. That's going to be less, let's see, what is it? That's going to be less than or equal to the max of fn of t, which is a positive thing, on t bigger than delta, with t in that minus pi to pi, times, this thing is less than or equal to m plus 2m, so I get times 2m here, times the length of the interval. Let's see, what the length of the interval would be delta minus pi minus delta plus the other one is pi minus delta also in length. Well, that's 2 pi minus 2 delta. Two pi minus 2 delta, and that's less than 2 pi. Okay, so I get some numbers on there, right, but I can make this as small as I want. I can make small as desired by choosing n big. This is the first time I had to choose n big. In the I1, I didn't have to care what n was, which is interesting. So I didn't do that, but now I need to do that. I can make as small as desired by taking n large enough, sufficiently large. In particular, I can make it, what do I need to make it less than? Make it less than epsilon over 2 divided by 2 times m times 2 times pi. And that would give me exactly what I need, namely then let's say n bigger than n naught would do that. Then the integral, that was representing sigma nx minus f of x is less than or equal to I1 plus I2, and they're both less than or equal to epsilon over 2. When n is bigger than that particular n naught. That's how you do it. And whenever you have a good kernel, you can do exactly that routine. It's the same thing every time. Okay, so this is a Fejér's theorem 2. Fejér's theorem number 2, which is a biggie. Trigonometric polynomials are dense among 2 pi periodic continuous functions. I can approximate things uniformly. So that there's a word for that. Denseness are dense among 2 pi periodic continuous functions. On R. That's a biggie. And this will have a huge consequence, namely that Bessel's inequality for Fourier series, at least, is actually an equality. So a huge consequence. I guess I should mention a proof here. The SNs, T's, are trig polynomials. Hence, so are the sigma T's. So are the sigma n T's. And the density just follows from the fact that the Fourier things, the Fejér things, converge to the function. But a huge consequence from this is going to be that Bessel's inequality becomes an equality. Tends to an equality as n goes to infinity. And that equality is called Parseval's identity. Let me show you why. We've done all the work for this. So why? Let's see, remember we would have 0. I did this calculation. This is the L2 norm of f minus, these are the Fourier coefficients here. Remember, this is the best approximation in L2 to f. So these are the Fourier coefficients, f hat of n. This was the best, this thing right here is the best L2 approximation of f among trig polynomials of degree n. So of the form summation an e to the I n x from minus n to plus n. That was the best one. So this would be less than or equal to f minus the sum as n goes from minus n to n of anything else. And those Fejér polynomials are of that form. So I would use the sigma n here. Okay. I can make that go to z. This would get within as close as I want. I can make this as small as I want. So phi nx goes to f uniformly. And that's just an integral from minus pi to pi. And so this goes to 0. As n goes to infinity. Okay, so that means that the Fourier. So the conclusion here is that the Fourier series converges in L2. This is where we see that the summation the Fourier the Fourier series converges to f in this Hilbert space of square integrable functions on minus pi to pi. That's what that means. That thing goes to 0. Okay. And remember when I did the calculation of that thing right there, let me copy it. No, I don't want to copy it. I want to, yeah. We're running out of time, all right. Sorry. Okay, this thing here, by making the Fejér current things go to the function as close as I want, I can make this less than epsilon for n bigger than n naught. And this thing, when I calculated the day I did Bessel's, this was f squared minus the sum of the Cn squared. I guess there's a 2 pi here because I didn't normalize them. Okay, and when you put that on the other side, you see that those things converge. So in the end, we see that the limit as n goes to infinity of the summation from minus n to n of Cn squared equals 2 pi times the L2 norm of f squared, which is 2 pi times the integral from minus pi to pi of f of x squared dx. And so, of course, this is the sum from minus infinity to plus infinity.